All right, let's get right into it. For as long as we've been around, we've lived with this terrifying fact. The ground we stand on can, at any moment, just completely betray us. No warning at all. But what if there's a pattern hidden in all that chaos? A kind of mathematical rhythm, a strange number that could actually tell us when the planet is about to break.
I mean, seriously, think about it. We see a hurricane forming out on the ocean, we track its every move with satellites, and we can warn people days ahead of time. But an earthquake? It's just bam! It arrives in an instant. A sudden, violent, terrifying rupture. So what makes them so fundamentally different, so unpredictable?
You know, the search for some kind of earthquake precursor is as old as our fear of them. People in ancient times looked for any clue they could find. Birds suddenly taking flight, weird lights in the sky, you name it. But even as science got more and more sophisticated, we've really struggled to find a single, reliable warning sign.
And that's true even today. With all of our incredible tech, we're talking GPS arrays, super-sensitive seismic sensors, massive supercomputers, we are still completely caught off guard. It's like these events are mocking our attempts to find some kind of order. For decades, they've just seemed totally random.
But this is where the story gets really interesting. A group of researchers started to look at this whole problem in a new way. Instead of hunting for one big, dramatic trigger event, they began digging through all the seismic noise, just looking for subtle, repeating patterns.
And guess what? They found something. Buried in these massive datasets, logging countless tiny tremors, they discovered what looks like a statistical fingerprint, a telltale number that seems to change as a fault system gets closer and closer to a catastrophic failure.
Okay, so to really get this, we need to decode the first and probably the most famous of these statistical clues. It's a value that comes from a really foundational law in the world of seismology.
It's called the Gutenberg-Richter law, and it's actually a pretty simple but incredibly powerful observation. Basically, in any given area, you get a whole lot of small earthquakes, a few medium-sized ones, and very, very rarely a really big one. And this relationship, it isn't random. It follows a beautiful mathematical pattern.
And here's the math that describes it. Now don't worry, your eyes don't need to glaze over, we're not doing a pop quiz here. The only thing you need to know is that n is the number of earthquakes and m is their magnitude. But the real star of the show is that little letter b, the b-value. That is the signature we've been looking for. It tells you the ratio of small quakes to big ones.
So what does a normal b-value look like? Well, pretty much all over the planet, it tends to hang out right around 1.0. What that means is, for every single magnitude 6 earthquake, you can expect to see about 10 magnitude 5s and about 100 magnitude 4s. It's a surprisingly consistent rule of thumb for how our planet behaves.
But here's the big breakthrough. That number, it's not always 1.0. Sometimes it changes, and when the b-value starts to drop, say down to 0.8, it's a huge warning sign. It means the fault is locking up, the stress is building, all the little quakes that release pressure stop happening, and the system is getting ready for one single massive rupture. It's like the quiet before the storm. This kind of behavior is a classic sign of something called self-organized criticality. The best way to picture it is to think of a sand pile. You add one grain of sand, then another, and nothing much happens, until you add that one final grain that triggers a huge avalanche. The Earth's crust might be doing the exact same thing, just building up stress grain by grain until it hits that critical tipping point. So, okay, the b-value is a powerful clue. It tells us that stress is building up. But it turns out that's not the only pattern hiding in the data. More recently, scientists found another, even more subtle signature, using a totally different way of looking at the numbers. This is where something called natural time analysis comes into play. Instead of just looking at when an earthquake happens on a clock, this method focuses on the order of the events and how much energy each one releases. It's like listening for a change in the rhythm of the planet's heartbeat as it gets closer and closer to that critical state. And what comes out of this analysis is our second strange number, 0.07. This is the critical value for a variable scientists call kappa 1. You can think of it as a measure of the order and fluctuation in the system. And what they found is that as a fault seismic activity pushes this value towards 0.07, it seems to be a universal signal that the whole system is about to fail. It's another red flag, a warning of an impending collapse.
So this all sounds pretty amazing in theory, right? But does it actually hold up in the real world? Have these numbers actually appeared before major disasters?
Well, the evidence is pretty compelling.
When researchers went back and looked at the data from some of the biggest earthquakes in recent history, the patterns were there. Before the Loma Prieta quake in California, before the devastating Kobe quake in Japan, they found significant drops in the B-value. And before the catastrophic 2011 Tohoku quake in Japan, studies found weird signals in both the B-value and that critical kappa 1 number.
And what's really cool is that we can actually reproduce this in a lab. Scientists take rock samples, they squeeze them under incredible pressure, and the rocks start to emit these tiny acoustic pings. They're like microearthquakes. The statistics of those pings follow the exact same Gutenberg-Richter law, and right before the rock shatters into pieces, its B-value plummets. This is huge. It suggests the physics of failure is the same whether you're looking at a small rock in a lab or a giant tectonic plate.
Okay, so if these numerical patterns are so promising, you gotta be asking, why aren't we issuing earthquake warnings and evacuating cities? Well, like with any cutting-edge science, it's just not that simple.
See, the Earth's crust isn't some clean, perfect sample in a lab. It's a messy, chaotic, unbelievably enormous system. Stresses shift, fluids are moving around down there, temperatures change, and what looks like a clear pattern today might just vanish tomorrow. So while these numbers are definitely significant statistically, they aren't nearly precise enough yet to bet millions of human lives on them.
And all this complexity is actually changing the entire goal of earthquake science. It's shifting the focus away from that old dream of being able to perfectly predict an earthquake.
The old goal was all about answering the question, when and where will the next big one hit? The new goal is to answer a different and maybe more useful question. How close is a specific fault system to its breaking point? It's less about having a crystal ball and more about creating a kind of stress map, a weather forecast for the Earth's crust.
And here's where it gets truly mind-bending. These statistical patterns, these strange numbers, they're not unique to earthquakes. Scientists are seeing them pop up everywhere, in the behavior of solar flares, in the way avalanches happen, even in the firing patterns of neurons in our own brains. It's almost like it's a universal language for how complex systems organize themselves right on the edge of chaos.
So in the end, we may never be able to predict the exact moment an earthquake will strike, but we're starting to understand the hidden math that governs them. We're learning to read the planet's vital signs, not as a prophecy of what's going to happen, but as a probability of what could happen. And that just leaves you wondering, right? What other chaotic parts of our world are secretly dancing to the rhythm of a universal number?